Hello, and welcome to the AstroGuy Podcast. I'm your host, Wayne Zuhl. In this episode, we're diving into one of the most impressive recent achievements in amateur astronomy. But before we get to that, I just want to remind you that you can still enter our 1,000 subscriber contest to win a free autographed numbered print. So check out that video and be sure to leave your comment before November 25th. Now moving on to the focus of the episode, Saturn is already a spectacular target, but this year it offered something truly special, a series of rare Titan transits when Saturn's largest moon crossed directly in front of the planet. These events only happen during narrow windows every 15 or so years, and capturing even one of them takes careful planning and excellent conditions. Our guest today captured not only one, he imaged 15 out of the 16 Titan transits. That's an extraordinary accomplishment. He's one of the most enthusiastic and active amateur astronomers that is doing real science today. Recently, he was recognized by ALPO, the Association of Lunar and Planetary Observers, as their recipient of the 2025 Walter A. Haas Observer Award. We're joined by planetary imager Greg Shanos, whose dedication, technical skill, and persistence have produced one of the most complete amateur records of this transit season. We'll talk about how he planned the project, the equipment he used, the challenges he faced, and what these transits can teach us about Saturn and its moons. So settle in. This is a fascinating look at the power of amateur astronomy and the passion behind a truly remarkable project. Greg, welcome to the AstroGuy Podcast.
I'm very happy to be here with the AstroGuy. And I'd just like to give this presentation. There was a few months ago a historic series of Titan shadow transits on Saturn. Now that Saturn's rings are edge on, the moons are going through the disk, just like Jupiter. So we're seeing a lot of shadow transits, and a lot of the smaller moons like Dione and Tethys, you can barely see the shadow, but Titan is really large. And so there was a historic series from April 29th, 2025 to October 6th. Every 16 days, there was a shadow transit. And the thing is, this was only visible from the Western Hemisphere because it's given in universal time. So in the Eastern Hemisphere, this was during the daylight. So that's why they didn't see it. But we were able to see it in North and South America. And the rotational period of Titan is 15 days and 22 hours. And so every 16 days, it would come around, okay? And so I only learned about this the first week of May, so I missed April 29th. And once I heard about it, I made it my mission to attempt to observe every single transit, okay, from that point on. So that would be 10 of them from May 15th through October 6th. And so I missed the April 29th, and I was like, kicking myself for it. And then I did a simulation. This is a program called WinJupos, which is free. And just Google WinJupos, and it tells you here the time in local time and universal time. For my time in Sarasota, so 10 hours, 21 minutes, this thing would have started, but at 10 hours, 54 minutes, here it is. So it's right on the ring plane. Here's the shadow, here's Titan. It's right on the ring plane. And sunrise was a 6:52, so this is a 6:54. So this is in the daylight, all right, with the sun up. So I wouldn't have seen this anyway. So that kind of made me feel good. So then I focused on getting the rest of them. So this is the equipment I use. I have a Meade LX200 GPS, 10-inch, and I'm equatorially mounted. And for planetary, is total different animal than deep sky astrophotography. The thing is, for planetary, you're taking a video and you're isolating all the individual frames. So normal motion is 30 frames per second. So these fast cameras here can take like 150 frames per second. So it could take a lot of frames per second. And then you have programs that isolate those frames and align and stack, and I'll talk more about that later. But this is the equipment I use here. So I use a ZWO 462 monochrome, and this is the quantum efficiency graph. And remember, visible light is between 400 and 700 nanometers right here. Okay, this is what the eye can see, 400 to 700. And here is ultraviolet, and past 700 is infrared. And in planetary, if the seeing is not good, all right, seeing the turbulence in the atmosphere, okay, you want to use infrared wavelengths because they're less affected by atmospheric turbulence, and this will give you a sharper image. Okay, so it's preferred to use infrared, and if you look at the quantum efficiency graph here, I use a beta 610 nanometer filter. So I'm still in the red part in the visible 610, and then I go into the infrared, and then notice how sensitive it is. We get 90% quantum efficiency here from 700 on, okay? And here from 700 nanometers, I have like 75% quantum efficiency. So getting good, this is a pretty sensitive camera. And if you're doing visible color, you would want to use a UV-IR cut filter because you want to cut out everything past this because it makes the image a lot softer. You can't get as sharp an image, and you want to cut out the rest here in the ultraviolet. So the ultraviolet goes from 3 to 400 that this is sensitive to. So the infrared, they're a lot more sensitive, these cameras, to these CMOS chips, to the infrared, all right? But in this case, you want the infrared, okay? That's my equipment, and here I use an MSI computer. It's a gaming computer, and I like gaming computers because I have no idea how to play game. I'm not a gamer, but it has high-end graphic cards and RAM and components which you need in doing video processing. And when you're playing the game online, you basically video, it's all live video, so you need that high-end stuff. So, and I upgraded this to 40 gigs of RAM. I added another 32 gig card into this and got 40. So, and it's i7, and it has 6 cores and 12 threads. So it's a nice computer. Okay, and then this is the software I use. There's 2 types of software you can use for actually acquiring the image. There's SharpCap and Fire Capture. Both are free, but the SharpCap, there's a professional version, which is only $18 a year. I prefer Fire Capture over SharpCap. And you need to acquire an uncompressed video, so you can't use MP4, okay? These programs only work with either AVI or SCR videos, okay? And SCR is actually the more preferred one to use. So I use the SCR for mono, and I tend to use the AVI. I think it works a little better for color, one-shot color. So these are both uncompressed formats here. And then Auto Stacker, which is in the 4th version now, the beta, this aligns and stacks each individual frame from the uncompressed video. This is free. And then input it into Registack 6, which is an older program, hasn't been updated since 2011, but it has these wavelets, which are fantastic for sharpening. So once the aligned and stacked video is put into Registacks, these wavelets sharpen it further, okay? So that's what that's for. And then there's this other program which I like called Astra Image. It's a one-time cost, $79.95. And this has a nice deconvolution algorithm. So I use Lucy Richardson deconvolution, just apply a little bit. It's up to version 6 now. I don't use 6 because the 6 has AI in it, and you don't want any AI when you're dealing with planetary, because you don't want to introduce any false information to it. Okay, you're doing more science here. And to sharpen it a little bit further, I have Photoshop CS12 when you actually buy Photoshop, and now it's a subscription based. But I use what's called a high pass filter, which does some additional sharpening and final touches. And then GIMP is a free program. I gotta play with this a little bit and see what it is. But if you don't want Photoshop, you can always use GIMP. Okay, so this is basically the software for acquiring the images, aligning and stacking, sharpening, and then sharpening and final touches. Okay, and then I need to add one more here. Jupos does a derotation, so it takes a lot of these final images and it puts them all together, so it actually reduces noise even more. So okay, so typical observing condition. This is what I had most nights. Okay, so out of my 10 observations, 6 out of 10 looked exactly like this. Okay, now no one in their right mind would be imaging, even planetary under these conditions. Okay, but since this was a special event, I'm very tenacious, and I'm not giving up. And if you look carefully here, there's Saturn. See, and then here's the moon. So that's another nice thing about planetary is you can have the moon nearby the planet and it doesn't matter. You try imaging a galaxy with the moon this close, it's not going to happen. So this was most, and there's an old expression in Florida: if you don't like the weather, wait a minute, because it changes very rapidly. Fortunately, these clouds were moving very quickly. See, you can see little pockets here. See how it's thinner here and thinner. So I just waited until it got to here, and then I took a video. All right, and then once it started getting, behind the clouds, then I'd stop. Okay, so that's basically my conditions. So it was pretty bad. So here's the results under these kind of conditions. Okay, this is what I got. Isn't that amazing? So the saving
Really
grace of all this was that the seeing was good. See, so I have here all the scientific information. The telescope, the camera, the filter I use. I use a very low power Barlow. Okay, most people use 2 and 3x Barlow. I like a very low power Barlow because it's much easier to work with, I find. So the overall scene was above average, and the transparency was very poor through clouds. And something really paradoxical happens in planetary astrophotography is when the transparency is just perfect. I had a few nights ago, I was imaging Jupiter. It was a perfectly clear night, crystal clear, and the seeing was horrific. It was like this. I just packed it up and didn't bother. Okay. And then under conditions like this, where it's hazy and cloudy and humid, the seeing is better. It's amazing. The turbulence in the atmosphere is not so bad. It's actually was above average. It was very, very steady seeing. That's why I was able to catch all this. See, and you can see here that the weather conditions were better because you can see the belts and zones. See how that's a lot sharper than that? I'm using the same processing techniques. It's the fact that this was under better seeing conditions. Transparency conditions than this was. Okay. And then let's see, and here you couldn't see the rings because the clouds were so thick. See, these three were the worst, and here it was better. Okay, so these three were conditions like this. Okay, but I never gave up, and I ended up getting it. But if you look here, see where the shadow is? Here's Titan, and here's the shadow. Okay, notice how it's above this ring plane, and notice how it would have been on the 29th that I wasn't aware of. See, so you would not have seen it. It would have blended in with this. And plus it was daylight, the sun was up, you know. So here it's just slightly above it. Okay. And then notice each 16-day later, it's a little bit higher. And then it's a little bit higher still. See that? And then a little bit higher still, higher, and even higher than that. See that? And this halo around it is a artifact of processing. So that's not. But notice you can tell that the alignment is very good, because if the scene was bad, see how round the shadow is. That shadow would be oval, football shape, and would be very fuzzy and blurry. Okay, and then you start getting little lines going through here and here. So, and you don't. If you were to blow this up, the pixels are beautifully aligned. Okay, and that's because of seeing. Okay, transparency is, how clear the sky is, with clouds and everything. So this was very poor through clouds. What makes this unique, why I call it a historic series, is because this will not happen again till 2040. All right, so 15 years from now. So that's going to be amazing, and I want to be in my early 80s. So it's going to be, it's really something. That's why I call it a historic. And I'm not sure it's going to be like this, or if the Western Hemisphere is going to see it. I did an internet search, and there's no information on it. I guess because it's 15 years down the road, so nobody's really having much info on it. But here we go. So now it's even higher, see it? And higher still, and now it's and notice it's coming closer. This moon here is Dione, and what happened here is, I'll never forget this night. It rained, it downpoured rain at 11:30 the night before, which was September 3rd, and then on September 4th at about 1:30, the clouds just cleared, and I was able to image. I only lost 37 minutes coming in, and then right here, the clouds came back in, completely clouded over, and there was a shadow transit of Dione starting. If you look carefully here, you may be able to see a little hint of a shadow, but I missed that because it completely clouded over. But the main thing was, the shadow transit of Titan. And then this was the ultimate. On September 20th, look at that. So this is at 121. Okay, look at that. That's Titan itself. It was actually crossing along with the shadow. So it was just beneath the shadow. That's the shadow, and that's Titan itself. Isn't that cool? All the other ones know that Titan is above somewhere, see? And that was the last one. It was like a graze. It just nicked it a little bit. And that was the very last one on October 6th. And then another thing to notice too is the angular diameter increases too. See here, you're 16.4 seconds. And I'm using the exact same configuration, so the image scale is not changing. And if you look here, you can definitely tell it's larger. And then here, it's larger still to 19.4. And then this actually occurred when Titan was just below its shadow on day before opposition. So the opposition was September 21st. And then if you look carefully here, you can see that's a little storm, a little white spot. So ALPO's been monitoring, I've been helping monitor this white spot, and now it's finally disappeared. But it was visible all through October. Isn't that cool? See, so there's a lot of science in planetary astrophotography. Okay, and then this is a breakdown of my seeing conditions. So this was above average. 5 would be average, I put. and then anything 5 is below average. And then same thing here, 5 would be average transparency, 10 would be perfectly clear. Look at this, 3 through clouds, thick clouds, thick clouds. Look at these are the worst images here, and then here it was clear. All right. And then what I do is take 75-second videos, okay? And then I get about 4,000 frames from that. And then I line and stack them and sharpen and all that. And then what I do is I make little templates. And I made a series of 6. So I would label it O1, shadow approach it, on disk. And I will have about 8 of those. So I can 10 minutes when I derotate. Then 2, I'll say shadow approaching center, and I'll have another 8 in there. And then I'll have number 3, I'll have another 8 in that folder, centered and all that. See, so, and then at the end I have 6. So these are all the videos I took. So I took a total of 605 videos. I have 75 individual images of everything. And the total is 978 gigabytes of data. I have almost a terabyte of data. And I'm not deleting this because, like I said, this is historic. And you can actually see and I post my images online on this website, Planetary Virtual Online Library. So here's the Planetary Virtual Observatory and Laboratory here website, and I've submitted 649 images in about 4 or 5 years. So I'm really active in this, and you can click on any one of these images. Here's the color image, and you can see. So this is what I mean by a template. So what I do is I list here, this is a one-shot camera. I rotate it 10 minutes. Give the magnitude, diameter, phase, altitudes 57 degrees above the horizon, scene transparency. This is the date in universal time, the filter I use. Oh, and CM1, 2, and 3. Okay, what does that mean? These are central meridian longitudes. So it's just the same for Jupiter also. Since Jupiter and Saturn are gas giants, they rotate at a differential rate. So the center, the equatorial area, which is CM1, rotates the fastest, okay? So that has a different value. And then the top and the bottom here is CM2. And CM3 is the center, is kind of the core, how that is rotating. Okay, I don't know how they get this, measure this. And so if I go back, and then I can get, here's Jupiter. Now, Jupiter in the methane band, you use different filters. Look at that. Doesn't that look exotic? That looks like an alien planet, doesn't it? That's CH4. You have to use a specialized filter, 89 nanometers, plus or minus 18 nanometers. Isn't that cool? There's the red spot. See, isn't that cool? That's Jupiter methane band. Yeah, I know. It looks totally exotic to me, And then Jupiter in the ultraviolet. This looks similar to what you're seeing visual. So that's ultraviolet wavelength. So this is between 320 nanometer, 380. And then Jupiter in the red, which is this is infrared. See, it looks very similar to visible. And then Venus looks really cool. Venus, the clouds become visible in this, in the ultraviolet. So the clouds are actually dark because there's a unknown ultraviolet absorber there. So it absorbs ultraviolet, so it appears dark. So what you see here are the actual clouds of Venus, and these change every day, and they're not predictable. So and there was a spaceship around a spacecraft thing, Japanese spacecraft. It just went dead, unfortunately. So it was taking beautiful images of the cloud bands of Venus. But that's actually what got me into this. So that's just a sample of some of my images. I submitted 649 and growing. So my goal is to hit 700 by the end of the year. And at the rate I'm going, I'll reach it. So these are my conditions, all right? And, no one would be, imaging through clouds, but this was such a special historic event that's what I did. And what happened is if it was clear, I went from beginning to end. See it? So when it first touched it, see that? Isn't that cool? So from beginning to end, and then I made an animation. So there's the animation of the August 19th, and then this is September 4th. So this is from beginning to end. So I just don't observe it one snapshot in time. I want to get it from the very beginning, the ingress to the egress, from beginning to end. That's it. See that? Isn't that beautiful? Look at that. And then here's, it was perfectly clear on this day, which was fantastic. Look at that. You can see there's Titan just right there. And that's basically it. So that's the end of the presentation.
Let me start with the basics. And how'd you get interested in astronomy to begin with?
Well, I was always interested in science, and I loved all the sciences, biology, chemistry, physics, pharmacist by profession. What happened is I graduated pharmacy school in 1984, and then I was living in Rhode Island then, and I saw in the Providence Journal, in the Parade magazine, it said, Comet Halley coming at you. So I'm like, Comet Halley's coming? Oh, wow, I gotta see it. So then they said, contact Dave Houston, skyscrapers, the Astronomical Society of Rhode Island. So I and left the phone number. So I called up and I left the number, that I'm interested in seeing the comet, and I'd like to see the observatory and all that. And I didn't hear back for 2 weeks. And then I found out he called me back and he said, "You're the first caller," and I was on my honeymoon. Yeah, so I went and I saw the observatory there. They have an 8-inch Alvin clock refractor built in 1878, housed in a real observatory dome that turns. I saw that and I'm like, oh my God, fantastic. And then I attended a star party and they had Schmidt-Cassegrain telescopes. I fell in love with this design. And actually, this is the preferred design to use for planetary astrophotography too, because you have a large focal length, 10 inches, 2,500 millimeters, and with a 2x Barlow, you get 5,000. You want high powers. What you want with planetary, that's the thing, as opposed to deep sky where you want wide field. So that's why the scene becomes so critical, because you're high power, so any turbulence in the atmosphere is going to be magnified, whereas when you're wide field, and when I image the moon, there's hardly any scintillation in the moon because it's half a degree wide. So it's like doing deep sky, you got a wide field. But when you have something that's 19 arc seconds in diameter, not half a degree, the atmosphere makes a big difference. So that's how I got into it. I just saw those telescopes and I met other people and then I just joined the club, and I just, that was it.
So when you were doing this,
Yeah.
where were you living at the time? You weren't in Florida then,
Oh,
were you?
no, I was in I was born and raised in Rhode Island, and what happened is I got married in 1990, and my wife had plans to move down to Florida, and I became part of the plan. so So, but I don't regret it because I love Florida. The weather's nicer, especially in the winter. The summers are hot and humid, I know, but the hurricanes are the worst thing, and they're getting
Yeah.
much worse now, But other than that, the advantage of being in Florida is twofold for astronomy. One, they don't call it the sunshine state for nothing. It's usually clear. In the summer, it's usually quite cloudy and rainy, but then after 2 a.m., it clears up. So by the time you get up in the morning, it's perfectly clear again. See, so you do get a high proportion of clear. And the other thing is, I live near the water, so you have what's called laminar flow. The atmosphere is very steady. The ocean, well, the Gulf of Mexico in my case, because I'm on the Gulf of Mexico and not the Atlantic end, like Miami's in the Atlantic end. It's very stable. In the Gulf of Mexico, there's not many waves at all, very, very water. And so that stabilizes the atmosphere somehow. The much steadier skies. If you saw the ones from Frank in New York, they were a lot noisier than mine. And from, and from Mike in Canada, because they don't have the steady skies that, that Florida has. So I'm in the ideal, mine's being up on a mountain, in Colorado or something. I have really ideal, observing conditions, being the weather being clear a lot of the time, and also the laminar flow, the steadiness of the atmosphere for planetary.
Yeah, there was a famous planetary imager that used to live down in, I'm trying to remember the city. It got destroyed in the
Don
hurricane.
Parker. Don
Parker.
Dr.
Yeah.
Yeah, Dr. Don Parker. Actually, he's the one that got me into this, into planetary imaging. It was a real funny story in early 2000, I think around, I don't know, 3 or 4. There was a grazing occultation of Mars with the moon. And so it was in Lehigh Acres, which is kind of near Fort Myers. So it was far, but not that far for me. So it was maybe an hour and a half drive one way. So I went down there, and this was before GPS and everything, so I had to use actual maps to find it. So we met in the middle of nowhere in this field, okay? And Andrew Chaikin was there, who wrote the book Man on the Moon and some other books. So I was in contact with him. He's the one that told me about it. And then I had a camcorder, and I was going to hook it up to my telescope and videotape it. And the camcorder died that night. So I was like, oh my God. But then I saw Don Parker had a van, and he had a 6 or 8 inch reflector, and he had a webcam hooked up to it. And then he had that hooked up to a laptop, and I could see it happening there. And I'm like, oh my God, what is this? I was so excited. I'm like, this is for me, So I got the name. It was a 2U Cam Pro 2, and then K3CCD Tools was what was used, to acquire the video. And then AutoStacker 2 was out at that time, and Registax was. And then, oh my God. And then, no, I think AutoStacker might not have been out. Registax did both of them. But it was like so easy. It was like you took a little video, you aligned and stacked, and you sharpened, and you got it. And I was like, my God, this is incredible. This is absolutely incredible. So once I went home that night, and that was a work day too. But that's how I met Don Parker. And then he told me all this stuff, and I watched it live in real time on the video screen, through a webcam. And now webcams are very slow. These planetary cameras are much, much better. But still, it was the beginning of it. And in my opinion, this is as revolutionary as Galileo turning a telescope up to the heavens. Because who would think to attach a webcam to a telescope and then connect it to a computer and take, you know what I mean, a video
and
of
created something called lucky imaging that didn't
and
exist until,
yeah. Isn't that amazing? I mean,
it really is.
That's as revolutionary as Galileo turning the telescope up to the heavens. So that's how it happened for me.
Your main setup now, you have, obviously, I'm guessing that the scope behind you is your favorite scope.
Yeah, that's the 10-inch. Yeah, that's the largest I have, the LX200 GPS. Rest in peace, Mead. I love it.
Thank you again, Greg, for sharing this amazing information. Sometime in 2026, I'm planning to have a panel discussion about telescopes, and Greg will be part of that panel, so be sure to look out for that. And I'll have links in the show notes where you can see Greg's images. Our next episode, which will be What's Up in the December 2025 Skies, will be out before the end of the month. Make sure that you check it out. Thank you again for joining us. I hope that you found it fun, informative, and inspiring. Most of all, I hope it encourages you to step outside and maybe tackle an observing or imaging project of your own. If you've got questions, feedback, or ideas for future episodes, I'd love to hear from you. You can email me at astroguypodcast@gmail.com or send a text or a voicemail to 973-404-0380. Please be sure to check out the AstroGuy Podcast group on Facebook and visit our YouTube channel for past episodes, observing tips, and bonus content. If you enjoyed this episode, please like, subscribe, comment, and share. It really helps us reach more people. And if you'd like to help financially, you can always buy us a cup of coffee. The link is in the show notes. Until next time, may your skies be clear. And as always, carpe noctem, seize the night. I'm Wayne Zuhl, and this was the AstroGuy Podcast. Thank you for listening. As always, your questions, comments, and suggestions are welcome. Keep wondering. Keep your eyes on the sky. Have fun. Carpe noctem. Seize the night.